Calculus, Chapter 4, Section 3, Area and Definite Integrals. First, we have Theorem 4 that says, let f be a non-negative continuous function over 0 to b, and let a of x be the area between the graph of f and the x-axis from 0 to x, where x is in between 0 and b. Then a of x is a differentiable function, and the derivative of a equals f of x. Basically what this tells us is that what we found in the last section, the derivative of the area function is the function of the curve. In other words, derivatives and integrals undo each other, and there's a relationship between the integral or the antiderivative and the area underneath the curve. In the last section, we dealt with definite integrals that went from 0 to a value, and we used geometry to accomplish it. Now we're going to look at how to deal with definite integrals for any interval, and we're going to solve them using antiderivatives. So here's the idea. If you've got this graph and you want to find the area between where x is a and x is b, basically what you would do is you'd find the area from where x is 0 to b, and from where x is 0 to where x is a, and then you would subtract the two. In other words, you would take the area from 0 to b minus the area from 0 to a. Okay, just like that. And that's really kind of what we're going to do. We're going to find the antiderivative, we're going to evaluate it at b, we're going to evaluate it at a, and then we're going to subtract the results. And that's all you do. So if we want to find the area under the graph of 1/5 x squared plus 3 over 2, 5, find the antiderivative, put in 5 for x. And by the way, when we do the definite integrals, you leave off the plus c, so don't put a plus c in there. Put in 5 for x, put in 2 for x, and subtract the two results. Pause the recording, give it a try, and resume to check your answer. Okay, so the antiderivative is going to be 1/15 x to the third plus 3x. And again, you can leave off the c, don't worry about the c, because when you would subtract the two values, the c's would go away. So what we then do with the 1/15 x to the third plus 3x is we put in 5, and then we also do it putting in 2, and we subtract the results, and we get 16 4/5. This one. Pause the recording, give it a try, and resume to check your answer. Okay, so we get x cubed over 3 plus x. Remember, we don't need to leave the c on there. We can assume that it's 0 and leave it off. Put in 2 and put in 1, or excuse me, -1, and subtract the results. And we get 6. And they said you can kind of count the squares there since they've given you the graph in this nice, neat grid. If you count the squares, you can see that your answer is correct. Now try these two. We're going to use the function in the previous example, so if you need to back up and check it, see what it was, and then try these two. Pause the recording, give it a try, and resume to check your answer. Okay, so from 0 to 5, we have 46 2/3, or 140 over 3. For B, we have 9 1/3, or 28 thirds. And then C, can you suggest a shortcut for B? Because the graph is symmetric with respect to the y-axis, you could integrate from 0 to 2 and then double the result. But this will only work if it's symmetric with respect to the y-axis. Okay, now let's try a word problem. You're going to do the same thing. Just read the problem over. You're going to take the antiderivative, calculate it at 5 and at 0, and subtract. Pause the recording, give it a try, and resume to check your answer. Okay, here we go. You get x to the 4th over 4, put in 5, put in 0, and you have your answer. So we have a definition. Let f be a continuous function over ab, and f be any antiderivative of f. The definite integral is, and you see our integral symbol there, the starting point's the lower number, the a, the ending point's the higher number. And basically it's the antiderivative at b minus the antiderivative at a. A lot of times when we're working it out, we'll use this kind of notation as our in-between step. We'll take the antiderivative, and this book puts brackets around it and then puts the B and the A above and below. You might see me do it slightly different in class. When I learned this, we didn't use a bracket. We just drew a straight line. Either way is fine. It's just a shorthand notation to remind you of what you're doing. These problems, pause the recording, give it a go, and resume to check your answer. So for A, our antiderivative is going to be x to the third over 3 minus x squared over 2. And then you see how we put 4 and -1 into those and subtract. For B, the derivative of e to the x is e to the x, and the antiderivative of e to the x is e to the x. So just put the numbers in. C, the antiderivative of the natural log of 1 over x is the natural log of x. Because our x's are going to go from 2 to 5, we don't need to worry about putting an absolute value in here, and we use the calculator to approximate our answer. How do you know if you should use the calculator or not? Usually it'll tell you if you need to round or leave it. And then D, we did have to put the absolute value in there because, again, you cannot take a natural log of a negative. So make sure you include the absolute value, and you see the answer there. By the way, it may seem strange that we have a negative value for an area. We're going to talk about that in a minute. It is possible. All right, try these out. For part C, I would split it into x over x minus 1 over x. Pause the recording, give it a try, and resume to check your answer. Okay, you see how they look here. This is what's called the fundamental theorem of integral calculus. Fundamental as in foundational. If a continuous function f has an antiderivative capital F over a or b, it's really just what we just said. This is just officially making it, this is fundamental, this is foundational to the calculus that we are doing now. And that's kind of what this is a statement. All right, try this example. You got 1 over x squared. I would make that x to the minus 2. Pause the recording, give it a try, and resume to check your answer. And you should have gotten 0.9. Sometimes the function will dip below the x-axis like it is here. When this happens, the area in that portion is going to be negative because the y values are negative. You can calculate the area of this function in two ways. You can go from 0 to 1, figure that out, and that's going to give you a negative area, and then 1 to 2 on this one, and that'll give you a positive, and then add it together. Now, you actually don't have to go through all that trouble, though. If you use the method we've been talking about and just take the integral from 1 to 2, you're going to get the same answer, and it'll take care of it. So consider this function. It says, first of all, look at the graph and predict the sign result. In other words, do you think that this area will come out positive or negative? Will the negative part of the graph overwhelm the positive and make the answer negative or positive? And then evaluate it. Pause the recording, give it a try, and resume to check your answer. Okay, the graph looks like this, and it looks to me like the negative is overwhelming the positive. So the answer we would expect to be negative, and when we do the problem, we do get negative 2 1/4. Okay, now word problem. Northeast Airlines has determined that marginal profit resulting from the sales of X seats on a jet traveling from Atlanta to Kansas City and hundreds of dollars is given by this function. Find the total profit when 60 seats are sold. So to go from marginal to total, we need to take the antiderivative, and we're going to figure that out for 60. Pause the recording, give it a try, and resume to check your answer. Okay, so we're going to integrate, and then we're going to go from 0 to 60. And when we do that, that accounts for our loss, because there's going to be a time when if you don't sell enough tickets, you're actually taking a loss all the way into profit. And at 60, we get negative 50.1613. So they're actually losing money on the flight if 60 seats are sold. Okay, in acceleration, another physics problem here. Suppose a particle's acceleration is a of t equals 12t squared minus 6. The initial velocity is 5 meters per second, so when t is 0, v is 5. In the initial position, when t is 0, The position is 10. Find S of t. Now, what you're going to have to do is 2 steps here. You have to start with A of t. You need to backtrack to V of t. So you're going to find the integral, the indefinite integral, but you're going to use the initial condition that V of 0 is 5, and that will give you a definite equation for velocity, and then you need to backtrack that and find a definite equation for position. Okay, pause the recording, give this a try, and resume to check your answer. So we integrate A of t, and we get the velocity. It's 4t to the third minus 6t plus c1, which they're calling our constant, that. But then we're going to solve for it, and we get 5. So we have 4t to the third minus 6t. 5. We're going to integrate that, and we're going to get t to the fourth minus 3t squared plus 5t plus our second constant, which we will solve for using the initial condition that when t is 0, position is 10, and we get 10. And then after 2 seconds, we're just going to put in 2 for the time into that equation and get 24. Okay, Juanita's car is traveling at 40 miles per hour or 58.67 feet per second when she applies the brakes. The velocity t seconds after she applies the brakes is negative 1.197 t squared plus 58.67, where v of t is in feet per second and t is between 0 and 7. How far did it travel while she was braking? Okay, this is going to be one of those where we need an accumulated distance. Pause the recording, give it a try, resume to check your answer. Okay, so we're going to take the integral of the velocity from 0 to 7, and we find that while she was braking for those 7 seconds, she traveled a distance to 273.83 feet. What we just talked about, you might want to pause and look over this, and then resume to do some practice problems. Okay, pause the recording to try these problems and resume to check your answer. Continue this way through the rest of the recording.